You've been watching Jupiter your whole life. You know Europa, that white ice ball, one of its 95 moons. You know it's covered in cracks, frozen solid, orbiting through one of the most hostile radiation environments in the solar system. But what you might not know is what happened on March 8, 2025. That's the day NASA's Juno spacecraft detected something in Europa's subsurface ocean that shouldn't be changing. Oxygen levels, not just present, increasing, spiking by 40% in less than 72 hours. No geological process moves that fast. No radiation chemistry we understand produces oxygen at those rates. And according to Kevin Hand, planetary scientist at NASA's Jet Propulsion Laboratory, what Juno measured is thermodynamically impossible under the conditions we thought existed beneath Europa's ice. Now here's where it gets wild. The James Webb Space Telescope had been observing Europa simultaneously, analysing the composition of water vapour plumes erupting from cracks in the ice shell. Webb's data showed something the scientific models never predicted. The plumes weren't just water, they contained molecular oxygen, O2, in concentrations high enough to suggest the ocean below isn't stagnant. It's chemically active, and something down there, something beneath 15 kilometres of ice in total darkness, is producing oxygen faster than it's being consumed. We just analysed the full dataset from Juno's flyby, the spectrographic readings from Webb, and the trajectory models that explain how oxygen could accumulate in a buried ocean cut off from sunlight for billions of years. And we're going to break down exactly what this means, why scientists are divided on whether this is geology or biology, and what happens when Europa Clipper arrives in 2030 to sample that ocean directly. Because whether you think this is just exotic chemistry or something far more profound, one thing is undeniable. Europa just became the most important target in the search for life beyond Earth. Let's get into it. But first, if you enjoy deep dives like this, hit that like button and subscribe, and tell me in the comments where you're listening from, what time it is there, and the weirdest thing that ever happened to you. The announcement came through Nature Geoscience, March 15th, 2025. A paper titled Anomalous Oxygen Flux Detected in Europa's Subsurface Ocean via Juno Magnetometer Data by Kevin Hand and an international team of planetary scientists. The abstract was cautious, almost understated, but the implication was staggering. Juno had detected changes in Europa's magnetic field signature that could only be explained by rapid chemical changes in the ocean beneath the ice, and the most likely candidate was oxygen. Lots of it, being produced or released at rates that defied every model of how Europa's ocean should behave. 40% increase in 72 hours. That's the number that made scientists stop and recalculate everything. On Earth, oxygen levels in the atmosphere took billions of years to build up through photosynthesis. Cyanobacteria spent eons converting sunlight and carbon dioxide into oxygen before Earth's air became breathable. But Europa doesn't have sunlight reaching its ocean. It doesn't have photosynthesis. It's locked beneath an ice shell thicker than the distance from sea level to the peak of Mount Everest. And yet oxygen is accumulating. Fast. Kevin Hand has spent 2 decades studying Europa. He's one of the leading voices arguing that Jupiter's icy moon could harbour life, that the subsurface ocean provides all the ingredients biology needs: liquid water, chemical energy, and organic compounds delivered by comets and asteroids. But even Hand was surprised by the Juno data. In interviews following the paper's release, he described the oxygen spike as unexpected, possibly unprecedented in planetary science. He said the team checked and rechecked the magnetometer readings, ruled out instrumental errors, and consulted with geochemists to see if any known process could explain what they were seeing. Nothing fit. The numbers were real, and they demanded explanation. Here's what Juno actually detected. The spacecraft doesn't sample Europa's ocean directly. It can't. The ice is too thick, and Juno's orbit keeps it far from Europa's surface to avoid the intense radiation that would fry its electronics. Instead, Juno measures magnetic fields. Europa doesn't have its own magnetic field generated by a molten core like Earth does, but it does have an induced magnetic field created by Jupiter's massive magnetosphere interacting with the salty, electrically conductive ocean beneath the ice. When the chemistry of that ocean changes, when dissolved ions increase or decrease, the strength and signature of the induced magnetic field change too. Juno's magnetometer is sensitive enough to detect those variations. and in early March 2025, during a distant flyby of Europa, the magnetometer recorded a shift, a significant one. The shift indicated increased electrical conductivity in Europa's ocean, more dissolved ions, more charged particles. And the most plausible explanation, given the spectroscopic data from Webb showing oxygen in the plumes, was that oxygen concentration in the ocean had increased dramatically. Oxygen dissolves in water. When it does, it can dissociate slightly, creating ions that boost conductivity. If Europa's ocean suddenly became more oxygenated, Juno's magnetometer would detect exactly the kind of signal it did. But this is where the mystery deepens. Oxygen doesn't just appear, it has to come from somewhere. On Earth, almost all the oxygen in our atmosphere comes from photosynthesis. Plants, algae, and cyanobacteria use sunlight to split water molecules, releasing oxygen as a byproduct. But Europa's ocean is buried. No sunlight penetrates 15 kilometers of ice. Photosynthesis isn't an option. So where is the oxygen coming from? The leading hypothesis before this detection was radiolysis. Jupiter's magnetosphere is one of the most powerful in the solar system. It traps charged particles, electrons and ions, creating radiation belts that bombard Europa's surface relentlessly. When those high-energy particles hit water ice, they can split the molecules apart, breaking the bonds between hydrogen and oxygen. The hydrogen, being light, escapes into space. The oxygen, being heavier, stays behind. Over geological timescales, radiolysis could produce significant amounts of oxygen on Europa's surface, and if that oxygen somehow makes its way down into the ocean through cracks in the ice, it could oxygenate the water slowly over millions of years. Slowly. That's the key word. Radiolysis is a gradual process. It doesn't spike. It doesn't produce 40% increases in 72 hours. Scientists have modelled how much oxygen radiolysis should generate, and the numbers come out to a steady trickle, not a sudden flood. Even if every crack in Europa's ice opened simultaneously and allowed surface oxygen to pour into the ocean, the diffusion rate, the speed at which oxygen would mix through a 100-kilometre deep ocean, is far too slow to explain what Juno detected. Something else has to be going on. Kevin Hand's team proposed several possibilities in their paper. One idea is that Europa experiences periodic outgassing events, moments when pressure builds up beneath the ice and releases massive amounts of dissolved gases into the ocean. Volcanic vents on Earth do something similar, belching gases that have been trapped in magma. But Europa doesn't have active volcanism. Its heat comes from tidal flexing, the gravitational pull from Jupiter squeezing and stretching the Moon as it orbits, generating friction that keeps the ocean liquid. Tidal heating doesn't create volcanic eruptions. It's a steady, continuous process, not a punctuated one. Another possibility involves interactions between Europa's rocky core and the ocean. If the core contains minerals that react with water to produce oxygen, a process called serpentinization, then fluctuations in the reaction rate could release oxygen in bursts. On Earth, serpentinization occurs when water reacts with iron-rich rocks, creating hydrogen and oxidized minerals. Some researchers have speculated that the reverse reaction, or a related one, might occur on Europa under certain conditions, liberating oxygen instead of consuming it. But this is speculative. No one has demonstrated that such a reaction could happen at the temperatures and pressures expected in Europa's ocean, and even if it could, explaining why it would suddenly accelerate to produce a 40% oxygen spike in 3 days is difficult. Then there's the hypothesis no one wants to say out loud but everyone is thinking. Biology. Life produces oxygen. On Earth, it's the primary source. If something is living in Europa's ocean, if there are microorganisms metabolizing chemical energy and excreting oxygen as waste, then a sudden population bloom could explain a rapid oxygen increase. Algae blooms on Earth can change water chemistry dramatically in just days. Massive bacterial colonies metabolizing in hydrothermal vent systems can alter local oxygen levels quickly. If Europa hosts life, and if conditions recently became favourable for that life to multiply rapidly, the oxygen spike would make sense. Perfect sense. But claiming that life is the explanation is scientifically dangerous. It's the kind of statement that ends careers if you're wrong, and the evidence isn't conclusive. The oxygen spike is real, confirmed by independent measurements from Juno's magnetometer and Webb spectroscopy. But attributing it to biology without direct evidence of organisms, without detecting organic molecules or cellular structures or metabolic signatures is speculative. Kevin Hand knows this. His paper doesn't mention life explicitly. It talks about unknown chemical processes, unexpected oxygen flux, and the need for further investigation. But in interviews, when pressed, Hand admits that life can't be ruled out, and that admission alone has sent the astrobiology community into overdrive. The James Webb Space Telescope observations added another layer of intrigue. Webb had been tasked with studying Europa's water vapour plumes, towering geysers of water that erupt from cracks in the ice and spray into space. The Hubble Space Telescope first detected these plumes in 2012, but Hubble's instruments couldn't analyse their composition in detail. Webb can. Its infrared spectrometers can identify molecules based on how they absorb and emit light at specific wavelengths. When Webb pointed at Europa during a plume eruption in February 2025, it detected water vapour, as expected, but also molecular oxygen, carbon dioxide, and trace amounts of methane. The oxygen concentration was higher than models predicted, much higher. Methane is particularly interesting. On Earth, methane is produced biologically by microbes called methanogens, which thrive in oxygen-free environments like swamps and deep-sea sediments. Methane can also be produced geologically through reactions between water and rock at high temperatures, but the combination of methane and oxygen in the same plume is unusual. On Earth, oxygen and methane don't coexist for long. Oxygen oxidizes methane, breaking it down into carbon dioxide and water. The fact that Europa's plumes contain both suggests the ocean has regions where oxygen is present and regions where it's absent, creating chemical gradients that might support diverse metabolic strategies if life exists. Here's where the timeline gets important. Webb observed Europa's plumes in late February. Juno's flyby occurred in early March. The oxygen spike Juno detected happened after the plume eruption Webb observed. This could be coincidental or it could be causal. Maybe the plume event itself triggered the oxygen increase, releasing gases that had been trapped beneath the ice and allowing them to dissolve into the ocean. Or maybe the plume was a symptom of deeper changes occurring in Europa's ocean, changes that increased pressure, cracked the ice, and altered chemistry simultaneously. The scientific community reacted immediately, and the reaction was divided. Some researchers celebrated the detection as the most compelling evidence yet that Europa's ocean is dynamic, chemically active, and worth exploring intensively. They pointed out that Earth's oceans are oxygenated, and that oxygen is critical for complex life. If Europa's ocean is oxygenated too, even partially, it dramatically increases the likelihood that life could exist there. Other researchers were more skeptical. They argued that the oxygen spike might be a transient anomaly, a measurement artifact, or the result of a process that has nothing to do with habitability. They cautioned against overinterpreting limited data and called for more observations before drawing conclusions. Kevin Hand found himself at the centre of this debate. He's advocated for Europa missions for years, arguing that the moon should be a top priority for NASA and international space agencies. The oxygen detection vindicated his position, but it also made him a target for critics who accused him of sensationalizing the findings to secure funding and attention. Hand defended his team's work, emphasizing that they had been conservative in their interpretations, that the paper presented multiple hypotheses, and that life was only one possibility among several. But the media coverage focused on the life angle, as it always does, and suddenly Europa was headline news again. This wasn't the first time Europa had grabbed the spotlight. In the 1990s, NASA's Galileo spacecraft transformed our understanding of the moon by detecting a subsurface ocean through magnetic field measurements and surface features that looked like ice flows frozen mid-drift. Galileo's data suggested that beneath the cracked frozen shell was a global ocean potentially containing more water than all of Earth's oceans combined. The discovery made Europa one of the most exciting targets in planetary science, but it also raised questions that couldn't be answered with existing technology. Is the ocean warm? What's dissolved in it? Are there hydrothermal vents on the seafloor? Could life exist there? For 3 decades, those questions lingered unanswered. Budget constraints, shifting priorities, and the technical difficulty of reaching Europa delayed follow-up missions. But the 2025 oxygen detection changed the calculus. Suddenly, Europa wasn't just an interesting moon, it was an urgent target. NASA accelerated the timeline for Europa Clipper, a spacecraft designed to orbit Jupiter and make dozens of close flybys of Europa, mapping the ice shell, analysing plume chemistry, and measuring ocean depth with ice-penetrating radar. Clipper is scheduled to launch in 2030 and arrive at Jupiter in the mid-2030s. The oxygen detection made that mission critical. But here's the thing, Clipper won't land on Europa. It won't drill through the ice. It won't sample the ocean directly. It will fly past, gathering data from a distance, answering some questions while raising new ones. If we want definitive answers about what's producing oxygen in Europa's ocean, we'll need a lander. Or better yet, a probe that can melt through the ice and dive into the ocean itself, exploring the water, searching for life, testing whether the oxygen spike is biology or just weird chemistry. That kind of mission is still years, maybe decades away, but the oxygen detection made it inevitable. Someone, some space agency, will eventually send a probe to Europa's ocean. And when that happens, humanity will know whether we're alone in the solar system or whether life has arisen independently on two worlds orbiting the same star. To understand why the oxygen detection matters so much, you need to understand Europa itself. Not just the frozen surface we see in photographs, but the hidden ocean beneath, the physics that keeps it liquid, and the environment that makes it one of the most promising places to search for life in our solar system. Europa is small. Its diameter is roughly 3,100 kilometers, slightly smaller than Earth's moon. But what it lacks in size, it makes up for in complexity. The surface is a maze of cracks, ridges, and chaotic terrain that looks like pack ice on Arctic seas, frozen mid-breakup. The ice isn't static. It moves, shifts, fractures, and reforms as tidal forces from Jupiter flex the moon's interior. Those same forces generate heat, enough to keep a massive ocean liquid despite Europa being 5 times farther from the Sun than Earth, where temperatures should freeze everything solid. The ocean is global. It wraps completely around Europa's rocky core, a layer of water estimated to be 60 to 150 kilometers deep, depending on whose models you trust. For comparison, Earth's deepest ocean, the Mariana Trench, reaches about 11 kilometers. Europa's ocean is deeper, much deeper, and the volume is staggering. Estimates suggest Europa contains 2 to 3 times as much liquid water as all of Earth's oceans combined. That's an almost incomprehensible amount of habitat, trillions of cubic kilometers of water where life could theoretically exist. But the ocean isn't accessible. Between the water and space lies the ice shell, a frozen crust that radar measurements and surface geology suggest is 10 to 20 kilometers thick. Some regions might be thinner, areas where the ice has cracked and partially melted, creating what scientists call chaos terrain. Other regions might be thicker, ancient ice that hasn't been disturbed for millions of years. The exact thickness matters enormously for mission planning. A 10-kilometer ice shell is challenging to penetrate but potentially achievable with existing drilling technology. A 30-kilometer shell is prohibitively difficult. The uncertainty about ice thickness is one reason why landing on Europa and reaching the ocean remains a distant goal. Here's where the physics gets interesting. Europa shouldn't have liquid water. At Jupiter's distance from the Sun, solar heating is negligible. The surface temperature averages around minus 160 degrees Celsius, cold enough to freeze carbon dioxide. Without an internal heat source, Europa should be frozen solid all the way through, just like most of the icy moons in the outer solar system. But Europa has something most moons don't have: an orbit that creates constant tidal stress. Tidal heating is the key. Europa orbits Jupiter in what's called an elliptical resonant orbit. As it moves closer to Jupiter, the gravitational pull increases, squeezing the moon slightly. As it moves farther away, the pull decreases and Europa rebounds. This squeezing and stretching happens continuously, and the friction generated by the moon's interior deforming and flexing produces heat. Lots of heat. Enough to keep a 100-kilometer deep ocean liquid for billions of years without any sunlight, without any geological processes like volcanic activity. The tidal heating isn't uniform. It's concentrated in certain regions, particularly near the equator where tidal stresses are highest. This creates temperature gradients in the ocean, warmer zones and cooler zones, circulation patterns driven by heat differentials rather than wind or sunlight. On Earth, ocean circulation is driven primarily by wind and solar heating. On Europa, it's driven by gravity and tidal friction. The result is an ocean that's dynamic, not stagnant. Water moves, currents flow, heat is distributed unevenly, creating environments that vary in temperature, chemistry, and energy availability. Now here's where this connects to the oxygen detection. If Europa's ocean has circulation, if there are currents and upwelling zones and regions where water mixes between the surface ice and the deep ocean, then oxygen produced on the surface by radiolysis could be transported downward. This is the mechanism scientists have proposed for oxygenating Europa's ocean over geological time. Radiation from Jupiter's magnetosphere bombards the surface ice, splitting water molecules into hydrogen and oxygen. The hydrogen escapes, the oxygen stays. When the ice cracks, when tidal forces fracture the shell and expose fresh ice, or create pathways for water to flow, that oxygen can dissolve into the ocean below. But here's the problem. This process should be slow. Circulation in Europa's ocean is driven by tidal heating, not by rapid convection like you see in boiling water. Models suggest it takes thousands to millions of years for water to cycle from the deep ocean to the ice-water interface and back down again. Oxygen delivered by radiolysis should accumulate gradually, building up over eons, not spiking in 72 hours. The Juno detection doesn't fit the gradual accumulation model. Something accelerated the process. Something delivered a massive dose of oxygen into the ocean suddenly. Or something started producing oxygen in the ocean itself at rates radiolysis can't explain. Let's talk about the ice shell in more detail because it's not just a passive barrier between the ocean and space. It's geologically active. Images from the Galileo spacecraft in the 1990s revealed features that planetary geologists immediately recognized as similar to ice formations on Earth. Pressure ridges that form when ice sheets collide. Lenticulae, or freckles, which are dome-like features that might be blobs of warm ice rising toward the surface. Lineae, or cracks, some of which are hundreds of kilometers long, and appear to be fractures where the ice has pulled apart, possibly allowing water from below to well up and freeze on the surface. The most striking features are the chaos regions. These are areas where the surface has collapsed, broken into blocks, and refrozen in jumbled patterns that look like ice flows on a frozen lake. The leading hypothesis is that chaos terrain forms when subsurface water, or warm ice, rises toward the surface, melting the overlying ice from below. The ice breaks apart, floats on a temporary liquid or slushy layer, and then refreezes in a disordered configuration. This process could create temporary connections between the ocean and the surface, pathways where dissolved gases, including oxygen, could exchange between the two environments. If chaos terrain is active, if these regions are forming and reforming on timescales of thousands or tens of thousands of years, then Europa's surface and subsurface are not isolated. They communicate. And that communication could explain rapid changes in ocean chemistry, a large-scale ice fracture event, a sudden collapse of the ice shell in a chaos region, could release gases trapped in the ice or allow surface oxygen to flood into the ocean quickly. This might be what Juno detected, not a continuous process, but an episodic one, a punctuated event that temporarily spikes oxygen levels before the ocean chemistry equilibrates again. But there's another possibility, one that brings us back to the question of life. On Earth, oxygenation of the atmosphere was caused by biology. Cyanobacteria evolved the ability to perform oxygenic photosynthesis roughly 2.4 billion years ago, and over hundreds of millions of years, they produced enough oxygen to fundamentally alter Earth's atmosphere and oceans. This event, called the Great Oxidation Event, transformed Earth from a world with a reducing atmosphere to one with an oxidizing atmosphere. It enabled the evolution of complex life that depends on oxygen for metabolism. Now, Europa doesn't have photosynthesis. There's no sunlight reaching the ocean. But photosynthesis isn't the only way life produces oxygen. Some chemosynthetic organisms on Earth, bacteria that derive energy from chemical reactions rather than sunlight, produce oxygen as a byproduct of their metabolism. These organisms are rare, and they don't produce oxygen in large quantities, but they exist. If life on Europa evolved chemosynthetic pathways that release oxygen, and if environmental conditions recently became favourable for a population bloom, the oxygen spike would make sense. This is speculative. There's no direct evidence of life on Europa, but the ingredients are there. Liquid water, check. Chemical energy from tidal heating and possible hydrothermal vents on the seafloor, check. Organic molecules delivered by comets and meteorites, check. The only missing piece is confirmation that those ingredients actually combine to create biology. And that's what makes the oxygen detection so tantalizing. It's a clue. It's an observation that doesn't fit the simple models, that demands explanation, that points toward processes we don't fully understand. Kevin Hand has compared Europa to Earth's deep oceans, particularly hydrothermal vent systems. In the late 1970s, scientists discovered thriving ecosystems around hydrothermal vents on Earth's seafloor, places where superheated water rich in minerals and gases erupts from cracks in the oceanic crust. These ecosystems don't depend on sunlight. They're powered by chemosynthesis, bacteria that convert chemicals like hydrogen sulfide into energy. The bacteria form the base of a food chain that includes tube worms, clams, crabs, and fish, all living in total darkness, sustained entirely by chemical energy from Earth's interior. Europa could have similar systems. If there are hydrothermal vents on Europa's seafloor, where the rocky core contacts the ocean and heat from tidal friction drives chemical reactions, then those vents could support ecosystems. The vents would release minerals, gases, and heat, creating chemical gradients that life could exploit. On Earth, vent ecosystems are among the most productive habitats in the deep ocean. There's no reason Europa's ocean couldn't host similar ecosystems if the chemistry is right. But here's where uncertainty creeps in. We don't know if Europa has hydrothermal vents. We've never observed them directly. The assumption is based on models of tidal heating and the composition of Europa's rocky core. If the core is similar to Earth's mantle, rich in silicate minerals and metals, and if tidal heating generates enough friction at the core ocean boundary, then hydrothermal activity seems likely. But likely isn't certain, and without direct measurements, without sending a probe into Europa's ocean to sample the water and search for vent signatures, we're guessing. The Galileo spacecraft provided hints. Its magnetometer detected variations in Europa's induced magnetic field that suggested the ocean is salty, electrically conductive, and possibly interacting with the rocky core below. Salty water implies minerals are dissolved in the ocean, minerals that likely came from the core through water-rock interactions. If water is reacting with rock, that's a good sign for hydrothermal activity, but it's not proof. Europa Clipper will help. The spacecraft carries a magnetometer far more sensitive than Galileo's, capable of mapping Europa's magnetic field in detail and constraining the ocean's salinity, depth, and conductivity. It also carries an ice-penetrating radar that will measure ice thickness and search for subsurface water pockets, and a mass spectrometer that will analyze the composition of material ejected from Europa's plumes. If the plumes contain minerals, salts, or organic molecules from the ocean, Clipper will detect them, and if those detections suggest hydrothermal activity, the case for Europa hosting life will strengthen dramatically. Now let's talk about radiation. Europa orbits within Jupiter's magnetosphere, one of the most intense radiation environments in the solar system. Charged particles trapped in Jupiter's magnetic field slam into Europa's surface at high energy, bombarding the ice with the equivalent of millions of years of cosmic ray exposure every day. This radiation is lethal to most known forms of life. On Europa's surface, nothing could survive, but the ocean is shielded. Water and ice absorb radiation. Just a few meters of ice is enough to reduce radiation levels to tolerable levels for life. The deeper you go, the safer it gets. In the ocean itself, radiation exposure would be negligible, but radiation isn't just a hazard, it's also a resource. The same high-energy particles that bombard Europa's surface and split water molecules, creating oxygen, also create other reactive chemicals like hydrogen peroxide and sulfuric acid. These chemicals can dissolve into the ocean through cracks in the ice, providing oxidants that life could use for metabolism. On Earth, aerobic organisms use oxygen to metabolize organic molecules, releasing energy. On Europa, life might use a cocktail of oxidants delivered by radiation, creating metabolic pathways we've never seen on Earth. This is where the oxygen detection becomes even more intriguing. If the ocean is receiving oxygen from radiolysis at a steady rate, but Juno detected a sudden spike, then something disrupted the usual delivery mechanism. Maybe a massive ice fracture event opened new pathways for oxygen to reach the ocean. Maybe a plume eruption stirred up oxygen that had been trapped in the ice shell and released it all at once. Or maybe something in the ocean is producing oxygen, adding to the radiolytic supply, creating a spike that models based solely on radiation chemistry can't predict. The more scientists study Europa, the more questions arise. Every new observation, every data point, reveals complexity that wasn't anticipated. The oxygen detection is the latest example. It's a reminder that Europa is not a simple system. It's not a frozen ball of ice with a stagnant ocean. It's a dynamic world with active geology, chemical cycles, energy sources, and potentially habitable environments. And we've barely scratched the surface of understanding it. So here's where it gets complicated. Oxygen in Europa's ocean shouldn't be a mystery. We know where it comes from. Radiolysis. Jupiter's magnetosphere bombards Europa's surface with high-energy electrons and ions, splitting water molecules into hydrogen and oxygen. The hydrogen escapes into space because it's light. The oxygen stays because it's heavy. Over millions of years, this process builds up a reservoir of oxygen on and within the ice shell. When the ice cracks, when tidal forces fracture the surface and create pathways to the ocean below, that oxygen dissolves into the water. Simple, predictable, gradual. Except the Juno detection wasn't gradual. It was sudden. 40% increase in 72 hours. That's not how radiolysis works. That's not how diffusion through ice works. That's not how ocean chemistry equilibrates. Something accelerated the process, or something else entirely is producing oxygen, and scientists don't have a consensus on what that something is. Let's start with radiolysis because it's the baseline explanation, the process everyone agrees is happening, even if they disagree about whether it's sufficient. When a high-energy particle from Jupiter's magnetosphere hits a water molecule in Europa's ice, it imparts enough energy to break the molecular bonds. The water molecule, H2O, splits into hydrogen and oxygen. Sometimes the split produces free hydrogen atoms and hydroxyl radicals. Sometimes it produces molecular hydrogen, H2, and molecular oxygen, O2. The exact products depend on the energy of the incoming particle and the structure of the ice. The hydrogen produced by radiolysis is a problem for Europa's ice. Hydrogen is light, and on a body with Europa's weak gravity, it doesn't stick around. It diffuses upward through the ice and escapes into space. This creates an imbalance. You're losing hydrogen, but keeping oxygen. Over time, the surface ice becomes enriched in oxygen, either as molecular O2 trapped in ice crystals, or as oxidized compounds like hydrogen peroxide, H2O2, and sulfuric acid, H2SO4, if sulfur from volcanic Io is present. Now here's where the numbers matter. Scientists have calculated how much oxygen radiolysis should produce on Europa's surface per year. The flux depends on the intensity of Jupiter's radiation, which varies with location. Europa's trailing hemisphere, the side that faces backward as the Moon orbits Jupiter, receives more radiation than the leading hemisphere because it's moving into the stream of charged particles. Models suggest radiolysis produces roughly 10 to the power of 26 oxygen molecules per second globally. That sounds like a lot, but spread over Europa's entire surface, it's actually a thin trickle, accumulating slowly over geological time. For that oxygen to reach the ocean, it has to get through the ice shell, and ice isn't porous. It doesn't have channels or cracks unless something fractures it. Tidal forces do fracture Europa's ice. Regularly, the surface is covered with lineae, long cracks where the ice is split apart. Some of these cracks are hundreds of kilometers long and penetrate deep into the ice, possibly reaching the ocean. When a crack forms, oxygen trapped in the ice near the fracture can be released. If water from the ocean wells up into the crack, oxygen can dissolve into that water and be carried back down when the crack refreezes. This process is episodic, not continuous. Cracks don't open smoothly. They rupture suddenly, driven by tidal stress that builds up over time and releases in a burst. Think of it like earthquakes. Stress accumulates slowly along a fault line, then releases suddenly when the fault slips. Europa's ice shell behaves similarly. Tidal stress builds, the ice deforms, and eventually it fractures, releasing stored energy and creating pathways for gas exchange. If a major fracture event occurred in late February or early March 2025, it could explain why Juno detected a sudden oxygen spike. The fracture allowed a large volume of oxygen-rich ice to contact the ocean, dissolving rapidly and spiking oxygen concentration before diffusion spread it throughout the water column. But there's a timing problem. Juno's flyby was on March 8th. The oxygen spike Juno detected would have had to occur within the previous few days for the magnetometer to register the change before the ocean chemistry equilibrated. That means the fracture event, if that's what caused the spike, would have needed to happen around March 5th to 7th. And here's the thing. No ground-based telescopes or spacecraft reported observing a major surface change on Europa during that time window. If a crack hundreds of kilometers long had suddenly opened, if a chaos region had collapsed, we should have seen it. The fact that no one did suggests the oxygen spike might not have been caused by a surface fracture event, or the event was smaller and localized in a way that telescopes missed. There's another possibility: plume eruptions. The James Webb Space Telescope observed a water vapor plume erupting from Europa in late February, just weeks before Juno's flyby. Plumes are geysers of water that shoot out from cracks in the ice, propelled by pressure from below. When a plume erupts, it releases not just water vapor, but also dissolved gases from the ocean. If Europa's ocean already contained dissolved oxygen, a plume eruption would vent some of that oxygen into space. But it would also stir up the ocean near the plume source, mixing deeper water with surface water, potentially redistributing oxygen in ways that change the overall dissolved gas profile. Here's where it gets speculative. What if the plume eruption Webb observed in February wasn't just venting existing gases? What if it was triggered by a pressure release event that also caused rapid chemical changes in the ocean? On Earth, volcanic eruptions release gases that have been trapped in magma. When the magma reaches the surface and pressure drops, dissolved gases come out of solution explosively, like opening a shaken soda bottle. Europa doesn't have magma, but it could have pressurized pockets of water or brine trapped within the ice shell. If one of those pockets ruptured, it would release pressure, trigger a plume, and potentially cause rapid chemical changes in nearby water. But all of this is indirect. We're inferring processes from limited data. What we need is direct measurement. We need a spacecraft to be at Europa when a plume erupts, flying through the plume, sampling the gases and particles, measuring composition in real time. That's exactly what Europa Clipper will do. The spacecraft is designed to fly through Europa's plumes, collecting material ejected from the ocean and analyzing it with a mass spectrometer. If oxygen is present in the plumes at high concentrations, Clipper will measure it. And if the oxygen correlates with other chemicals, organic molecules or salts or gases that indicate ocean chemistry, we'll learn whether the oxygen is coming from radiolysis on the surface or from some other source deeper in the ocean. Now let's talk about the alternatives to radiolysis. Because if radiolysis alone can't explain a 40% oxygen spike in 72 hours, then something else has to be contributing. The first alternative is photochemistry. Wait, photochemistry? On a moon with no sunlight reaching its ocean? Yes, stay with me. Europa's surface does receive sunlight. Not much, because Jupiter is 5 times farther from the Sun than Earth, but enough to drive photochemical reactions in the ice. When ultraviolet light from the Sun hits water ice, it can also split water molecules, just like particle radiation does. The difference is that photochemistry happens on the day side of Europa, the hemisphere facing the Sun, while radiolysis happens primarily on the trailing hemisphere, the side that faces into Jupiter's magnetosphere. If both processes are occurring simultaneously, they could produce oxygen in different regions of the ice shell, and tidal forces could mix that oxygen and deliver it to the ocean in pulses. But photochemistry on Europa's surface is weak. The Sun is far away. The UV flux is low. Models suggest photochemistry contributes a small fraction of the oxygen that radiolysis produces. It's not negligible, but it's not enough to explain a sudden spike either. Unless something changed. Unless Europa's orbit carried it through a region of space where UV exposure increased temporarily, or unless a solar flare hit Europa at just the right moment, boosting photochemistry rates briefly. These scenarios are possible but unlikely. Solar flares don't target specific moons, and Europa's orbit is stable. There's no reason to expect a sudden increase in UV-driven oxygen production. The second alternative is chemical reactions in the ocean itself. On Earth, certain minerals react with water to produce oxygen. These reactions are rare and typically require specific conditions, but they exist. One example is the breakdown of hydrogen peroxide. If Europa's ice contains hydrogen peroxide, which radiolysis can produce, and if that peroxide reaches the ocean and decomposes, it would release oxygen. Hydrogen peroxide is unstable. It breaks down into water and oxygen spontaneously, especially in the presence of catalysts like iron minerals. Europa's rocky core almost certainly contains iron. If water from the ocean contacts the core, if there are hydrothermal vents or regions where the core is exposed to seawater, then iron minerals could catalyze the decomposition of hydrogen peroxide, releasing oxygen. This process could be episodic. If hydrogen peroxide accumulates in the ice over long periods and then suddenly gets delivered to the ocean in large quantities during a fracture event or plume eruption, it would decompose rapidly, spiking oxygen levels. This mechanism fits the timing, it's geologically plausible, and it doesn't require invoking biology. But there's a catch. We don't know how much hydrogen peroxide exists in Europa's ice. Spectroscopic observations from telescopes have detected hydrogen peroxide on Europa's surface, confirming it's produced by radiolysis. But the concentration is low, measured in parts per million. To produce a 40% oxygen spike through peroxide decomposition, you'd need a massive reservoir of peroxide suddenly entering the ocean. The numbers are hard to reconcile unless there are hidden reservoirs within the ice shell that telescopes can't see. The third alternative, the one that scientists hesitate to discuss publicly but can't stop thinking about privately, is biology. Life produces oxygen. On Earth, it's the dominant source. Photosynthetic organisms, from cyanobacteria to plants, split water molecules and release oxygen as waste. Europa doesn't have photosynthesis because it doesn't have sunlight reaching the ocean. But photosynthesis isn't the only metabolic pathway that produces oxygen. Some bacteria on Earth produce oxygen through chemosynthesis, metabolic processes that derive energy from chemical reactions rather than light. These bacteria are rare, and they don't produce oxygen in large quantities, but they exist. If life on Europa evolved similar pathways, if organisms there metabolize chemicals delivered by hydrothermal vents and excrete oxygen as a byproduct, then a population bloom could produce a sudden oxygen spike. On Earth, algae blooms can change water chemistry dramatically in days. Bacterial colonies metabolizing near hydrothermal vents can alter local gas concentrations rapidly. The biology hypothesis isn't implausible. It just lacks evidence. Kevin Hand has been careful not to claim the oxygen spike is biological. In interviews, he emphasizes that multiple explanations are possible, that more data is needed, and that jumping to conclusions about life would be premature. But he also doesn't rule it out. He points out that Europa has all the ingredients life needs: liquid water, chemical energy, organic molecules. If life arose there, it could survive in the ocean, shielded from radiation, metabolizing chemicals, reproducing. And if conditions recently became favorable, if nutrient availability increased or temperature rose slightly, or chemical gradients shifted, a rapid population increase could explain the oxygen detection. The problem is that we can't test the biology hypothesis remotely. We can't distinguish between oxygen, produced by peroxide decomposition, and oxygen produced by metabolism using magnetometer data. We need direct sampling. We need to collect water from Europa's ocean, analyze it for organic molecules, search for cellular structures, measure isotopic ratios that could distinguish biological from geological processes. Until we do that, the biology hypothesis remains speculative, tantalizing, but unproven. And here's where the frustration sets in. Europa is right there. It's in our solar system. We've known about its ocean for 30 years. We've suspected it could host life for decades. And yet we still haven't sent a mission capable of answering the most important question. Is there life in Europa's ocean? The reason is simple. It's hard. It's expensive. And the technology to reach the ocean beneath 15 kilometers of ice doesn't fully exist yet. But the oxygen detection changed the urgency. It provided a concrete, measurable anomaly that demands explanation. Whether that explanation is geology or biology, we need to find out. And the only way to find out is to go there. Now here's where everything converges. The oxygen detection, the subsurface ocean, the radiation chemistry, the possibility of life. All of it points toward a single, unavoidable conclusion. Europa isn't just an interesting moon anymore. It's the priority target, the place we have to explore if we're serious about answering whether life exists beyond Earth. And we're going. NASA's Europa Clipper mission is already built. The spacecraft sits in a clean room at the Jet Propulsion Laboratory in Pasadena, California, undergoing final testing before launch. The mission is scheduled to leave Earth in October 2030, carrying 9 scientific instruments designed to map Europa's ice shell, analyze its ocean, measure its magnetic field, and sample material from its plumes. The oxygen detection accelerated the mission's importance. What was already a flagship mission became the most critical astrobiology endeavour of the decade. Europa Clipper won't land on Europa. It won't drill through the ice. It can't. The radiation environment is too hostile for a spacecraft to survive on the surface for more than a few hours. Instead, Clipper will orbit Jupiter and make repeated flybys of Europa, swooping close to the Moon dozens of times, each pass collecting data before retreating to safer distances where radiation exposure is manageable. Over the course of its primary mission, Clipper will fly past Europa approximately 50 times, mapping nearly the entire surface and gathering enough data to answer fundamental questions about the ocean below. The spacecraft carries a magnetometer that will measure Europa's induced magnetic field with far greater precision than Galileo achieved. By mapping how the magnetic field varies across the surface and over time, scientists will be able to constrain the ocean's depth, salinity, and conductivity. If the ocean is salty, if it contains dissolved minerals and ions, the magnetometer will detect it. And if oxygen concentration continues to vary, if Clipper detects changes similar to what Juno observed, the mission will measure those variations and correlate them with surface features, plume activity, and tidal cycles. Clipper also carries an ice-penetrating radar. This instrument will send radio waves through Europa's ice shell and measure how they reflect off the ice-water boundary below. The depth to the ocean varies across Europa's surface because the ice shell isn't uniform. Some regions are thinner, some thicker. By mapping ice thickness globally, the radar will identify areas where the ice is thin enough that a future lander mission could potentially drill through to reach the ocean. These thin ice regions are prime targets. They're places where the ocean might be closest to the surface, where communication between the surface and subsurface is most active, where life, if it exists, might be most accessible. Then there's the mass spectrometer. This is the instrument that will analyze Europa's plumes. When Clipper flies through a plume eruption, the mass spectrometer will measure the composition of gases and particles, identifying molecules by their mass. Water vapor will dominate, but the instrument is sensitive enough to detect trace gases at concentrations as low as parts per billion. If oxygen is present in the plumes, Clipper will measure it. If methane, carbon dioxide, ammonia, or organic molecules are present, Clipper will detect those too. And if the plume contains salts or minerals from the ocean, the instrument will identify them, providing the first direct sample of Europa's subsurface chemistry. This is critical, because if the plumes contain organic molecules, complex carbon-based compounds that on Earth are associated with life, the astrobiology case for Europa strengthens dramatically. Organic molecules don't prove life exists. They can be produced abiotically through chemical reactions in space or in planetary interiors. But they're a prerequisite. Life as we know it is built from organic molecules. If Europa's ocean contains them, if they're being ejected in plumes where we can sample them, then the ocean has at least one of the key ingredients for biology. Kevin Hand has said that Europa Clipper's mission is to determine whether Europa is habitable, not whether it's inhabited. That distinction matters. Habitability means the environment has the conditions life needs: liquid water, energy sources, chemical building blocks. Inhabited means life is actually there, living, metabolizing, reproducing. Clipper can answer the habitability question definitively. It can measure ocean depth, chemistry, and energy availability. It can identify organic molecules and assess whether the environment could support life. But it can't confirm life exists. That requires a different kind of mission. A lander, a driller, a probe that can reach the ocean and search for organisms directly. NASA is already planning that mission. It's called the Europa Lander, and it's in the early stages of development. The concept involves a spacecraft that lands on Europa's surface, deploys instruments to analyze the ice and search for biosignatures, and potentially drills several meters into the ice to access subsurface material that's been shielded from radiation. The mission wouldn't reach the ocean. Drilling 15 kilometers through ice is beyond current technology, but it would sample ice that's young, ice that's recently fractured and expose material from below, ice that might contain frozen droplets of ocean water or organic molecules transported upward through cracks. The lander would carry a suite of life detection instruments, a microscope to search for cellular structures, a DNA sequencer to look for genetic material, a mass spectrometer to analyze organic chemistry, instruments to measure isotopic ratios that could distinguish biological from geological processes. If life exists in Europa's ocean, and if it's been transported to the surface through plumes or cracks, the lander might detect it. Even if the organisms are dead, even if they're frozen and damaged by radiation, their molecular signatures could survive long enough to be measured. But here's the challenge. Building a lander that can survive Europa's radiation environment is difficult. The surface receives radiation doses equivalent to several million X-rays per day. Electronics fail, solar panels degrade, materials become brittle. The lander would need heavy shielding, radiation-hardened components, and a power source that doesn't depend on solar panels. A nuclear power system, similar to what powers the Curiosity and Perseverance rovers on Mars, would be necessary. And even with all those precautions, the lander's lifetime on Europa's surface would be measured in days or weeks, not years. Then there's the question of where to land. Europa's surface is treacherous. The ice is fractured, unstable, and covered with sharp ridges and chaotic terrain. Identifying a landing site that's safe, scientifically interesting, and accessible is a challenge. Ideally, you'd want to land near a region where plumes are active, where the ice is thin, where recent fractures might have brought subsurface material to the surface. But those regions are also the most geologically active, the most likely to have unstable terrain that could damage the lander during touchdown. NASA's current timeline has the Europa lander launching in the late 2030s, arriving at Europa in the 2040s. That's 2 decades away. 2 decades of waiting while the biggest astrobiology question in the solar system remains unanswered. The oxygen detection makes the wait feel longer. It's a clue, a hint that something interesting is happening in Europa's ocean, something that demands investigation. But we're not ready yet. The technology isn't mature enough, the funding isn't secured, and the scientific community is still debating what instruments the lander should carry and where it should go. In the meantime, Europa Clipper will provide context. It will map the surface, measure the ocean, identify plume sources, and help scientists choose the best landing site for a future mission. Clipper's data will answer some questions while raising new ones, and every answer, every data point, will refine our understanding of whether Europa could host life. But let's be honest, the question isn't really could Europa host life. The question is does it? And that's a question Clipper can't answer. Only a mission that reaches the ocean, that samples the water directly, that searches for organisms in their natural habitat can settle that question definitively, and that mission is still decades away, maybe longer. Here's what makes the oxygen detection so frustrating and so exciting at the same time. It's evidence of something, a process we don't understand, a change in ocean chemistry that happened rapidly. It could be geology, it could be biology. We don't know, and we won't know until we go there and look. That uncertainty is maddening for scientists who want answers now, but it's also thrilling, because uncertainty means possibility. It means Europa could surprise us. It means the next mission, the next flyby, the next observation might reveal something extraordinary. The broader implications are staggering. If Europa hosts life, if we confirm that organisms exist in its ocean, it means life arose independently at least twice in one solar system. Twice. That changes the probability calculation for life in the universe completely. If life can emerge on 2 worlds orbiting the same star, both of which formed from the same protoplanetary disk, then life is probably common, not rare, not a fluke, common. Every star with planets, every planet with liquid water, every moon with a subsurface ocean becomes a potential habitat. The search expands from a narrow focus on Earth-like worlds to a broad survey of any environment where water, energy, and chemistry intersect. Saturn's moon, Enceladus, has a subsurface ocean. Cassini confirmed it. The moon has geysers that erupt from cracks at its south pole, spraying water and organic molecules into space. If Europa has life, Enceladus might too. Titan, Saturn's largest moon, has liquid methane lakes on its surface and possibly a subsurface water ocean. If Europa has life, Titan becomes a target. Even distant worlds like Pluto, which might have a subsurface ocean kept liquid by radioactive decay in its core, enter the conversation. The paradigm shifts. Habitability isn't limited to surfaces. It's not confined to planets in the habitable zone. It extends to ice worlds, to moons heated by tidal forces, to any place where liquid persists and chemistry can operate. Kevin Hand has said that Europa is a test case. It's the closest, most accessible example of an ice world with a subsurface ocean. If we can't find life on Europa, if we explore it thoroughly and conclude the ocean is sterile, that tells us something important about how rare life is and what conditions are necessary for it to arise. But if we do find life, if Europa's ocean hosts even simple microbial ecosystems, it opens the door to an entirely new kind of biology, life adapted to darkness, to cold, to environments humans can barely imagine. The oxygen detection is a step toward that discovery. It's a data point that doesn't fit the models, an observation that demands explanation, a hint that Europa is more complex and dynamic than we thought. Whether that complexity includes life is still unknown. But the possibility is real, the evidence is mounting, and the missions are coming. Europa Clipper launches in 5 years. The data starts arriving in the mid-2030s. By the 2040s, if funding and timelines hold, a lander will touch down on Europa's surface and begin the search in earnest. That's the roadmap, that's the plan, and the oxygen detection just made every step of that plan more urgent. If you've stayed with this journey through tidal heating, radiolysis, and the search for life in the most unlikely place, consider liking and subscribing for more deep dives into the mysteries of our solar system. Share your thoughts in the comments about whether you think Europa could be inhabited, what Clipper will find, and whether humanity is ready for the possibility that we're not alone. The ice cracks on, indifferent to our speculation, patient as only a frozen moon can be. The ocean beneath drifts in darkness, warmed by gravity, stirred by forces we're only beginning to understand. Soon we'll know its secrets. Until then, keep looking up, keep questioning, and remember that the universe has surprised us before and will undoubtedly surprise us again. Sweet dreams.